And once you start seeing physics this way, you realize that the mirror and the train are not isolated curiosities. They are representatives of an entire class of misunderstandings that arise whenever we confuse description with mechanism. The human mind is extremely good at inventing stories. It is much less good at noticing when those stories have quietly replaced reality. We tell ourselves that mirrors flip left and right because that's the story that fits our experience of people turning around. We tell ourselves that flanges guide trains because that's the story suggested by their shape. In both cases, the story works well enough to get us through everyday life, so we never bother to check whether it's actually true, but physics begins precisely at the moment when well enough is no longer enough. Physics begins when you ask, what is really doing the work here? And very often the answer is not the thing you're staring at most closely. It's the thing you didn't think to question. Take the mirror again. Imagine for a moment that instead of people, we were creatures who naturally moved by flipping front to back, rather than turning left to right. Suppose that with a normal weight bodies reoriented themselves in space. In that world, no one would ever say that mirrors reverse left and right. They might say mirrors reverse front and back, and they would be completely satisfied with that explanation. The confusion exists only because of the way human bodies happen to be built and the way we habitually move through space. This is an important lesson because it tells you that some puzzles are not puzzles about nature at all. They are puzzles about humans. They reveal more about how our minds work than about how mirrors work. And if you're not careful, you can spend a long time trying to fix nature when the real problem is your vocabulary. The same thing happens constantly in more advanced physics. Students struggle with time dilation, with quantum mechanics, with relativity, not because the equations are impossible, but because their everyday intuitions are sneaking in where they don't belong. They try to imagine electrons as tiny billiard balls, or time as a universal, ticking clock, or space as a passive stage where events happen. And then they're shocked when nature refuses to cooperate. The mirror is a gentle warning. It says, be careful. Your intuition is useful, but it is not sacred. Now let's return to the train for a moment, because there's more hiding there than just tapered wheels. The reason this example is so powerful is that it shows how stability can emerge from motion itself. The train not stable because it is rigidly locked into place. It's stable because it's allowed to move slightly. And that movement creates restoring forces. If the train were clamped rigidly to the track, it would be brittle. The slightest defect would cause a failure. Instead, it's free to wander a little, and that freedom is precisely what keeps. It's safe. This idea shows up everywhere once you know to look for it. A tightrope walker doesn't stay balanced by freezing perfectly upright. They constantly sway, making tiny corrections. Your body doesn't stand still when you're standing. It's always making microscopic adjustments. Even atoms in a solid are not fixed in place, they vibrate. A stability in nature often comes from motion, not stillness, the tapered. Railroad wheel is a beautiful mechanical embodiment of that principle. It doesn't fight motion, it uses motion. The sideways drift of the axle is not a problem to be eliminated, it's part of the solution. The very act of drifting generates the correction. And notice something else, the system doesn't need to know where the center is. There's no reference point, no sensor, no external measurement. The geometry itself defines the center implicitly. Wherever the axle is, the difference in rolling diameters creates a tendency to return toward equilibrium. The system carries its own reference frame inside its structure. That's a remarkably deep idea. In physics, we are often tempted to think that order requires supervision. We imagine that stability must be enforced. But many of the most stable systems in nature are stable precisely because no one is in charge. You can push this idea even further. Think about planetary orbits. A planet doesn't stay in orbit because something is constantly steering it. It stays in orbit because the laws of motion and gravity combine in just the right way. The planet is always falling, but it keeps missing. The motion itself sustains the structure. Or think about atoms. An electron doesn't sit still next to a nucleus. It exists in a dynamic quantum state. The stability of matter is not static, it's dynamic. The same theme appears again and again, from the smallest scales to the largest. And this brings us back, once more, to the mirror. Because the mirror, too, is revealing something about how deeply we rely on static pictures. We imagine a frozen snapshot, you hear, image there. And then we try to explain that snapshot using everyday categories. But what you are actually seeing is the result of a process. Light leaves your body, travels to the mirror, reflects, and returns to your eyes. The mirror image is not an object sitting behind the glass. It's a reconstruction, assembled moment by rays of light, obeying simple geometric rules. If you really wanted to be precise, you wouldn't say the image is behind the mirror at all. You'd say that the light rays behave as if they originated from a point behind the mirror, that as if is doing a lot of work. The image is a convenient fiction that helps us predict where the light will go. It is not a thing in space in the same way a chair is a thing in space. This distinction between real objects and useful fictions is another cornerstone of physics. We talk about electric fields, magnetic lines, virtual images, centers of mass. These are not objects you can pick up. They are conceptual tools. And they are incredibly powerful as long as you remember what they are and don't mistake them. For physical stuff, many confusions in science arise when we forget that difference. We argue about whether a wave function is real or whether a field exists, when often the better question is, what does this concept help us calculate? What does it predict? What mistakes does it prevent? The mirror image is one of the first places where this lesson quietly appears in everyday life. The image feels real. You react to it emotionally. You adjust your hair by watching it. But physically, it is nothing more than a pattern of light rays. And that's why the mirror problem is so us. E-full. It's a small puzzle that trains you to separate experience from explanation. Now, think again about how easily we were misled by the flanges on the train wheels. They look important, they are dramatic, they make noise when something goes wrong. So we give them credit. But the real work is being done silently by the taper of the wheel, something most people never notice at all. Physics is full of these quiet heroes. The most important part of a system is often the least conspicuous. In electrical circuits, for example, beginners focus on batteries and light bulbs, but the real story is in the electric field distributed throughout the circuit. In thermodynamics, people focus on engines, pistons, and flames, but the deep principles live in entropy and statistics. In astronomy, people marvel at stars, but the structure of galaxies is shaped by invisible dark matter. The mirror and the train are teaching you where to look. They are saying, don't be hypnotized by appearances. There's also a broader philosophical lesson here about explanation itself. A good explanation is not one that feels satisfying at first glance. A good explanation is one that continues to work when you change the situation. The mirror explanation that says left and right are reversed fails the moment you rotate yourself or lie down. The explanation that says the perpendicular direction is reversed works in every orientation. The flange explanation fails when you ask how trains survive long stretch. ES of track without constant scraping. The tapered wheel explanation works everywhere, all the time. In physics, robustness is everything. The right explanation is the one that survives abuse. This is why physicists love symmetry. Symmetry is a kind of stress test for explanations. If your explanation depends on a special orientation, a special observer, or a special frame of reference, it's probably incomplete. The mirror explanation that survives rotation is the symmetric one. The train explanation that doesn't care whether the track curves left or right is the symmetric one. And symmetry, once you start noticing it, becomes one of the most powerful guiding principles in science. Conservation laws arise from symmetries. The laws of physics look the same today as they did yesterday. They look the same here as they do on the other side of the galaxy. These are not trivial facts. They are deep structural features of reality. The mirror, in its own quiet way, is a symmetry machine. It enforces a very specific transformation and nothing else. And by watching how that transformation clashes with our expectations, we learn something about both physics and ourselves. By the time you've really absorbed these ideas, something subtle changes in the way you look at the world. You stop asking, what does this do? And start asking, what constraints is this obeying? You stop asking, who is in control? And start asking, what structure makes this inevitable? That shift from agency to structure is one of the hardest, but most rewarding transitions in learning physics. It's also why physics can feel unsettling. It replaces intention with law, purpose with pattern. But in exchange, it gives you explanations that are deeper, cleaner, and far more universal. And perhaps that's the quiet joy hidden in these simple puzzles. They take everyday experiences, looking in a mirror, watching a train go by, and turn them into gateways. They invite you to step outside your habitual way of thinking and see the world as it actually is, not arranged for our convenience, not aligned with our instincts, but astonishingly consistent, elegant, and honest